This NEET question given twice in 2020 in kinetic theory of gases is all about mean free path. It is just a formula, mean free path. So to solve these problems, I'll quickly derive the equation for that mean free path itself. Therefore, we can easily come to a kind of an answer, right? So let us first try to understand what is a mean free path. What is it? Gas molecules always have a random motion. So while each molecule is moving in a random motion, it collides with the other molecules that are come across in its path. So the mean free path, as the name itself, is the average distance traveled by a gas molecule between two successive collisions. So before it collides with someone else, it travels some distance. The average of all that is called as mean free path. So the question is, how do you calculate it? That's the question that we need to understand. So to understand how do we calculate it, let us consider a gas molecule like this. This is a gas molecule whose diameter is d. D is the diameter, right? So let us consider a gas molecule whose diameter is d. So there are so many gas molecules around its path. So if there is, imagine there is another gas molecule like this, who is also, all the gas molecules are identical in nature because it's an ideal gas. That is also D. This gas molecule is just in touch with the surface, therefore they can have a collision, right? Imagine this gas molecule is moving with a velocity v. So with whom this gas molecule can have a collision? If it is moving in a straight line, whatever the gas molecule comes in the path will have a collision with that. This molecule that I have drawn with a black color has come in touch with that, so we can assume like that's a collision. But if you imagine another gas molecule who is somewhere here, the distance between this center and this center is greater than d. So there is no collision with this gas molecule that I have drawn in the red color. But if I have drawn some another gas molecule, say purple, which is somewhere here, it could be anywhere. From this center to this center, this distance is less than that of the D. It is coming in the path, therefore there is collision. So what I can say is, all the gas molecules who are coming within the periphery of a given gas molecule will have a collision. But how do I explain that? To explain that, from the center of the gas molecule, let us draw a line whose radius is r. Be careful, I am drawing a line, a radius. Earlier I said diameter of each gas molecule is d, but now I am going to draw a cylinder whose radius is equal to d. This is d, this one, radius. Taking that as a periphery around it, if I draw a cylinder like this, our gas molecule that I have drawn in blue color moving with a velocity v will have collisions that with all the gas molecules within the cylindrical region, because the distance between them is less than d, as I have told you, r equal to d. So what we can say is here, all gas molecules within the imagined cylinder of radius d, where d is the diameter of a given gas molecule, will have collisions with base molecule that we have taken into consideration, who I have drawn in a blue color. Okay, that's taking that into if you understand that point, we can further go for the derivation and derive an expression for the main free path, right? So what's the point that I want to do is, the first thing that I want to do is the length covered by the gas molecule, that's in blue color, by gas molecule, that's the first molecule that I have drawn. In a small time delta t is distance traveled equal to velocity into time. I have assumed that this gas molecule is having a velocity v, so length covered becomes automatically v into delta t, right? Now let us also consider volume that it covers, volume covered by that gas molecule in delta t time. Volume can be written like volume of a cylinder is area of cross section into length, right? So area of cross section of this part of the cylinder, pi d square, because I have assumed that radius of that cylinder is d. So volume covered is pi d square, that is area of cross section, into length covered in delta t. But we have already proved that length covered in delta t equal to v into delta t. So that's the volume that it covers, right? Now, there are a certain number of gas molecules within this volume, right? So let us assume let number of gas molecules per unit volume equal to n, right? Then per unit volume, that is n, then I can find out the molecules in total volume. That implies what I can write is number of gas molecules in total volume is number of the gas molecules per unit volume multiplied by the volume. But we have already written what is the volume is, right? So number of the molecules per unit volume is n multiplied by the volume of that cylindrical part. But volume of the cylindrical part, we have proved it as pi d square and v delta t. So this value becomes n pi d square v delta t, where n is the number of molecules per unit volume, d is the radius, v is the velocity with which that gas molecule is moving, delta t is the time in which we are considering the motion of that gas molecule, right? That's the total number of the gas molecules in total time delta t. That implies number of gas molecules per unit time. Per unit time, when you say, I have to divide that with time. So this above equation has to be divided with time delta t. So this delta t gets cancelled. So it becomes n pi d square v. That's the number of the gas molecules per unit time, right? That number of the gas molecules per unit time is actually equal to number of collisions that happens per unit time. Why like so? Because this molecule that I have drawn in blue color, that was drawn in the beginning here, will have a collision with all the gas molecules within the cylinder, and this is the gas molecules that are there within the cylinder. Therefore, that many collisions will happen. It will have collision with each of the gas molecules in that volume. Therefore, that becomes the number of collisions that happens per unit time. That's the number of the gas molecules. So once we know the number of the collisions per unit time, we can further write average time interval between two collisions. So I want you to understand this carefully. This is number of collisions per time. Then the average time interval is nothing but the reciprocal of it. Say for example, in a second there are two collisions happen, then the number of the collisions becomes 2. Then time interval between each collision is half of that, reverse of that 2, that is 1/2, that is 0.5 second. Hope you understand that. In 1 second, if there are two collisions, then the time interval between each collision is a reciprocal of that. So, average time interval between two collisions is reciprocal of number of collisions per time. That is reverse of this. That is 1/n pi d square and v. That's the average time interval between two successive collisions. Then, once if you know average time interval, I have to calculate mean free path. We are working for that only actually. So mean free path is average distance traveled, as we have defined, between two successive collisions. Two successive collisions. We know distance traveled equal to velocity into time. So velocity into time is nothing but the average time that we have already derived. So velocity into average time interval between two successive collisions, I have derived it as 1/n pi d square and v. So this v and v will cancel. This is 1/n pi d square. That is what we are expected to calculate in this all case, mean free path. But there is a catch in deriving all this. What is that catch is, we assumed that all other gas molecules are at rest and only the first gas molecule is moving, between only one is moving. But that's not the case. But what happens? But practically all others are also moving. All other gas molecules are also having a random motion. Molecules are also moving with a velocity, right? So taking that into consideration, we can say actual mean free path. Taking that into consideration, we can write actual mean free path as 1/√2 has to be written in extra mathematically, n pi d square. That's the final formula that we can use. So if you look at the question, a mean free path dependence on diameter is inversely proportional to d square. Option A is correct. Expression for the mean free path is what? So the first option, that what we have derived 1/√2 n pi d square is the right answer, right derivation. So while making this derivation, as I have not derived this derivation while I am talking about kinetic theory of gases, I have taken this time to derive this derivation for you. So I want you to understand from where this derivation is coming. Therefore, solving this kind of the problems becomes easy. It's a little lengthy video. I want you to go through this video once again until you get it. And if you still have not got it, you can just comment so that I can clarify the point that you have not got it, right? Thank you for watching.